Okay, I'm hoping everyone can see my screen. So I'm going to be talking about providers and TLS. I'm going to cover what kind of integration can you achieve between libSSL and a provider. I'm going to go into a little bit of detail about TLS groups and what they are. I'm going to talk about the provider feature that we call capabilities, and then cover how you can use capabilities to implement TLS groups. Then we're going to do the same for signature algorithms, just talk about what they are, and then how you can apply the capabilities concept to implement signature algorithms in your providers. We're going to talk about Cipher suites and what you can do there. Talking about two different types of Cipher suites, those for TLS 1.2 and those for TLS 1.3, and how you need to treat them within a provider is slightly different. And I'm very quickly going to touch on quick at the end and what all of the above means in a quick context. So first of all, it's worth saying that libSSL is fully provider aware. The TLS implementation in libSSL obviously uses numerous different cryptographic algorithms to do what it needs to do, and all of those algorithms are supplied by whatever providers are loaded at the time. Symmetric ciphers do need some special provider-side support in order to be usable, but exactly what that is depends on the TLS protocol version, and I will cover that later. You may need your provider to declare the TLS groups that it wants to support for key exchange or key encapsulation if your provider won't be running at the same time as the default OFIPS provider. And again, I'm going to cover that in much more detail. Other algorithms in general don't need any particular TLS awareness when you implement them in your provider. Optionally, you can also declare support for key exchange and encapsulation groups that the default FIPS provider currently have no knowledge of. So they can be completely new, not currently supported as of today in OpenSSL. You can still add them in, and the same applies to signature algorithms. And again, I'm going to talk about that. So let's quickly just talk about TLS groups then and what they are, and before we talk about how you can support them in your provider. So TLS has this concept of supported groups, which is an extension which is added to the client hello in a TLS handshake, and is sometimes sent back from the server as well. There is a registry of these groups maintained by IANA, the Internet Assigned Numbers Authority. There's a link on the screen there to that registry, so you can go and have a look at it. So these are just basically well-known groups that are well understood and defined. Obviously, in order to be interoperable, both your client and your server needs to have the same understanding about what these things mean. And so that's why there's a central register of these things. Basically, each group contains parameters about how key exchange or encapsulation and information about how key exchange and encapsulation is to be done. And each group is associated with an algorithm. So, for example, it could be the ECDH algorithm, the elliptic curve Diffie-Hellman algorithm, or just the plain finite field Diffie-Hellman, or others. So, for example, we have the SecP256R1 group. You may know this as P256. It goes by a few different names, and that's just an elliptic curve that you can use with the ECDH key exchange algorithm. Another example is SecP384R1, also known as P384. That's a different elliptic curve, but can also be used with the same ECDH algorithm. We've got FFDHE2048. That's a finite field Diffie-Hellman group for use with the DH algorithm. Then we've got X25519. This is so there's the X25519 key exchange algorithm, and it has associated with it a group X25519, and it's a one-to-one correspondence. So there aren't multiple groups for that algorithm. You only have the one group, unlike ECDH, where there are multiple elliptic curves. So this is what a TLS group is. Each one of those groups also has a number associated with it, which is important because it's that number that gets passed around in the TLS protocol. So for P256 or SEC P256R1, the number is 23. For the 384 curve, its number is 24, and for X25519, it's 29. It's all defined in the registry in that link that I gave, so go and have a look at that. So just wanted to talk a little bit about how key exchange actually works in TLS. So the client and server determined between them a mutually supported group and algorithm. Both client and server generate a private value and a public value. So they calculate the public value from the private value. And then that public value is passed to the peer. Yeah, and that's called a key share in TLS. So at that point, each endpoint has a private value that it's generated itself and a public value that's come from its peer. And using those two pieces of information, they can generate a key. And both sides of the communication do the same calculation with their own private data and the public data from the peer, and they end up with the same shared key value. Any eavesdropper that sees those public values being exchanged can't generate that shared key value because they don't have access to the private data. So that's key exchange. There's also key encapsulation, which has a similar goal of making sure that both the client and the server end up with the same shared key. With encapsulation, essentially the key is passed from one peer to the other in some encrypted form. So it is possible for a provider to extend the capabilities of libsl and add new groups for key exchange or encapsulation. This is something that's used, for example, by the OQS provider in order to add post-quantum algorithms into libsl. And as well as adding new groups, you can just replace the existing ones with your own implementations if you so wish. Okay, so that's groups. I'm just going to talk about the capabilities feature, and then we'll talk about how they combine. So the providers have the ability to declare certain capabilities. These capabilities aren't TLS specific necessarily in concept, but as of today, the only ones we have are related to TLS. We have capabilities for TLS groups, and we have capabilities for TLS signature algorithms. It's entirely possible in the future we'll have new ones, and even ones which are nothing to do with TLS. So the default provider, as an example, declares support through these capabilities for P256, for P384, for X25519, and a whole list of other groups. They're all declared as a capability. And then libsl, once it's found out what capabilities its provider supports, it can then use the groups that it's learnt through that process for key exchange and encapsulation during the TLS handshake. So when do you need to use these capabilities in your provider? So it's typically in one of two situations. If you are expecting that your provider is going to replace the default ORFIPS provider, and it's going to be used in TLS, then you're going to probably need to declare these capabilities. You will need to declare these capabilities. If your provider is just going to be used alongside default and FIPS, so you're going to have default or FIPS loaded and your provider at the same time, then you don't need to declare the capabilities. Or the other situation is if you've got some completely new group that doesn't exist in default, doesn't exist in FIPS, libsl doesn't know anything about it, and and you want to add that new group and make it available for TLS, then you'll need to declare a capability in that case. So how do you do it? So there is this function provider get capabilities that your provider will need to implement, and it just is inserted into the OSSL dispatch array that Richard talked about earlier in his talk, and it looks like that on the screen. So it takes in a provider context, it takes in a capability name, a callback, and an arbitrary opaque argument. So you declare that within your provider, and at a certain point, libSSL will call it to find out what information it can learn about the capabilities that your provider supports. And it will pass in the name of a capability that it's interested in. So for TLS groups, the name is TLS-group. So if you want to implement this, then your provider is basically required to look at the capability name, check whether it's being asked about the TLS group capability, and then call the callback that's been passed to it with information about all the groups that it supports. So let's say, for example, your provider has support for the foo group and the bar group. It would call the callback twice, once for foo and once for bar. And the code might look a little bit like what's on the screen there. It checks to see if it's being asked about the TLS group capability, and then it calls it twice. Calls its callback twice, passes in data about the foo group, and passes in the arbitrary argument that it was supplied, and then it does the same for the bar group. So that data that we need to pass to that callback, what does it contain? So it has the list of things on the screen there: a group name, an internal group name, the name of a key manager that it's going to use, the IANA ID, that integer number or code point that I talked about, the number of bits of security, so that might be 128 or 256, the TLS versions it supports, and also an indication about whether the group is to be used for key exchange or key encapsulation. The name that you give should be the same as the name as it appears in the IANA registry. And the internal group can be what it's known to as the provider. For example, as I said earlier, that sec P256R1 group, that's what it's known to IANA, but internally you might know it as P256. The algorithm name should be a key management algorithm that supports either key exchange or key encapsulation. Must support one of those two. The group ID you talked about, that's the code point. Then we have information about the TLS versions that it supports, and that's described through the minimum TLS version that it supports, the maximum TLS version, and the same for DTLS, the minimum DTLS version and the maximum DTLS version that it supports. Where 0 has the special meaning of there isn't a minimum and a maximum, and -1 means it's not supported at all. So here's an example. Here I'm declaring a new group called foo. I'm assuming that in the IANA registry it's called foo-IANA, and it's internally it's called foo-group. And the key management algorithm name, so this is the key manager that Thomas was talking about, is called foo-alg. The IANA registry has defined it to have a code point of 508, and it's got 128 bits of security. It must be used in TLS version 1.3 or above, but there is no maximum defined, and it can't be used in DTLS at all. The ischem value is 0, so this is a key exchange group. If we would just set that to 1, if it was a key encapsulation group instead. So that's all you need to do for groups. Signature algorithms. So TLS has this concept, signature algorithms, also known as signature schemes in the TLS13 RFC. That's basically, it's the same thing. It's a signature scheme is just a newer name. It works in a slightly different way, but it operates in the same space. If you're interested in the technical distinction between the two, go and have a look at the TLS13 RFC. A signature algorithm, or a sigalg, defines what algorithm a TLS endpoint understands when creating and validating digital signatures. And again, there's a registry of these. These are well-known sigalgs, and the registry is available at the URL on the screen there. OpenSSL already has a built-in list of these. If your provider is just using one of those, you don't need to do anything special. The built-in sigalgs are always defined, so you don't need to declare a capability if you're just going to use one of the standard built-in ones. That's the case even if default and FIPS aren't loaded. They're just known to libSSL. But if you want to implement one that is not known to OpenSSL, you can plug it in. That's a bit more complicated. You will need a decoder to do that, so that it can read keys, for example, out of a certificate. And Richard's talk after mine will talk about encoders and decoders. It's likely you'll probably need an encoder I said to read private keys, but that should say to write private keys. But you're likely to need these things. But you don't actually strictly need an encoder. You absolutely need a decoder. So new signature algorithms, they're plugged in via a capability, in the same way as groups are. For ones which aren't already known to OpenSSL, so ones which we're plugging in, we only support TLS13 and above. And the signature algorithm capability name is TLS-sigalg. As I said before, only the ones which are completely unknown to libSSL do you need to declare. They come in two types. There's simple and composite signature algorithms. Simple ones just define an algorithm. It doesn't have a separate hash, so the algorithm just takes in the data to be signed and produces a signature out the back of it. And that can be any arbitrary data. A composite algorithm, on the other hand, it consists of two parts. There's an underlying signature algorithm and a hash function. Typically, the signature algorithm will only sign hashes. So if you have arbitrary data to sign, you run it through a hash, it produces a digest value, and then you sign the digest. So that's a composite algorithm. So an example of that is RSA PKCS1 SHA-256. So it's going to use the RSA underlying signature algorithm with PKCS1 padding, and it's going to use that in conjunction with the SHA-256 digest or hash. So for each one of these that we're going to create, we need a name, and like with groups, we might have an internal name. It could be different. There's an OID, so these are the sort of dotted decimal numbers that you see associated with these algorithms. It needs a code point from the registry, and we need to know the number of bits of security and the TLS versions that it's applicable to. For composite algorithms, we also need to know the underlying signature algorithm name and the hash algorithm name. So the signature algorithm name should match that as in the registry, and the internal name could be the same as the other name, but it could be different. And then you also, for composite algorithms, need to define the algorithms as they are known to the provider. You can optionally provide a key type name, which could be different, but otherwise it's assumed to be the same as the signature algorithm name. So let's put that into an example. Here's the foo signature algorithm. So we are assuming that in the registry there is something called foo-IANA, and underneath it This is a simple signature we're doing here. So there's an underlying signature algorithm called foo-sig, and it's associated with that OID, and it's got a code point which is 65024. It's got 128 bits of security, and the minimum TLS version it supports is TLS 1.3. For plugged-in signature algorithms, we only support TLS 1.3 or above. Well, TLS 1.3 because we only support TLS 1.3 at the moment. But in the future, if TLS 1.4 came along, we'd be able to support that as well. And then we have a composite signature algorithm example. So it looks very similar, where again, we're assuming that there's this signature algorithm in the registry called foo-SHA-256 IANA, which has the same internal name. It's got an OID associated with it, and it's a composite algorithm. So there's an underlying signature called foo-sig, and it's got a hash, which is SHA-256. Actually, the hash doesn't have to come from your provider. It could come from default. So you could supply the definition of foo-sig, and you could just get SHA-256 from the default provider if you wish. It's got a code point. It's got 128 bits of security. And again, this one only supports TLS 1.3 and above. The reason DTLS doesn't exist here is because we don't support DTLS for plugged-in signature algorithms. We obviously do for the built-in ones, but not for plugged-in ones. There's documentation on the capabilities, and if you have a look at the capabilities section on that man page. Okay, I'm going to talk a little bit about Cipher suites now. So a Cipher suite is basically a collection of related algorithms that an endpoint is going to use to secure communication with its peer. There's quite a big difference between Cipher suites in TLS 1.3 compared to TLS 1.2 and below. In a TLS 1.3 Cipher suite, you're basically just specifying the symmetric cipher. So, for example, AES 128 in GCM mode, and an associated hash. So, SHA-256, for example. A TLS 1.2 Cipher suite, on the other hand, it specifies those same things, but additionally, it also specifies the key exchange and signature algorithm to use. So it's quite a bit more complicated. We don't currently support the concept of dynamically adding completely new Cipher suites to libSSL. You're stuck with the ones that we support that are already built in. It's possible at some future version that we could add that, but right at the moment, we don't do that. What you can do, though, is replace the underlying symmetric cipher that's used, so with your own implementation, if you want to. So you just need to make sure your provider is preferred for that algorithm when the SSL context is constructed. And then there's a few hoops that you need to jump through. It's a lot more straightforward for TLS 1.3 Cipher suites than it is for TLS 1.2. So I'm going to talk about TLS 1.2 first. Your cipher, your symmetric cipher, needs to be built with TLS in mind. It needs to have specific support for TLS. And importantly, it needs to support these two settable parameters. The OSSL cipher param TLS version parameter and the OSSL cipher param TLS max size parameter. All symmetric ciphers that are going to be used in cipher suites will have those as settable params. If the set param call fails when it tries to set those parameters, then the TLS connection will fail, which is why you need to be able to support them. The TLS version is given as an integer value. So TLS 1.3, for example, is the value 0304 in hex, and that's as it's defined in the RFC. Just a little bit of terminology. So the max size could be 0 if there isn't a MAC. Otherwise, it will be a positive value. But it could be 0 in the case that an AEAD cipher is being used. So if you're not familiar with this, AEAD is authenticated encryption with additional data. It's associated with particular cipher modes. So, for example, GCM mode or CCM mode are AEAD ciphers. And they basically combine a symmetric cipher and a MAC into one algorithm. The data to be fed into the MAC will come from the data that you're encrypting, or you can also feed in additional data, which is the AAD, the additional authentication data. And these ciphers, they produce obviously the ciphertext, but they also produce a tag, which is then used during decryption to verify that the data hasn't been tampered with. So AAD ciphers have a tag instead of having a separate MAC. So this is why the MAC size will be 0, because the tag is sort of built into the cipher. Okay, so if you want to replace the symmetric cipher for a TLS 1.2 cipher suite, you do it differently for AEAD ciphers compared to non-AEAD. So I'll talk about AEAD first. So as well as the 2 settable parameters that I already talked about, you also need to support the settable parameter OSSL cipher param AEAD TLS1 AAD. So this supplies the additional authentication data for a TLS record. And you also need to supply the gettable parameter, you support the gettable parameter OSSL cipher param AEAD TLS1 AAD pad. And that just returns the tag length to be used. If you're implementing either the GCM or CCM ciphers, then there's this other settable parameter, OSSL cipher param AEAD TLS1 IV fixed, which is the fixed portion of the TLS IV. There's 2 parts to the IV. There's a fixed portion and a per record IV. You combine them together to create the IV. You need to be familiar with the TLS1.2 spec for this. Okay, so if you receive one of these, the AAD or the IV fixed parameters, then you're in TLS 1.2 and below mode for your cipher. I'm going to talk about that in a minute as to what that means and how you need to treat that. But if you receive them, you're in TLS 1.2 mode. Okay, for cipher suites which are you just using plain symmetric ciphers, the non-AEAD ciphers, it works slightly differently. The first thing to note is no such ciphers are in TLS 1.3. So if you're implementing a symmetric cipher and you get this TLS version parameter, then you're automatically in TLS 1.2 and below mode. You additionally need to support the OSSL cipher param TLS MAC parameter. It's only used during decryption, and it's the provider's responsibility to return a pointer to the location in the decryption buffer where the MAC starts. So what does TLS 1.2 and below mode look like? How is it different to normal encryption and decryption? Okay, so TLS records are encrypted and decrypted in one go. The entire record is passed to your provider in a single cipher update call. Encryption and decryption is always in place. So that means the input buffer and the output buffer are the same buffer. The length of that buffer includes any IV if it's applicable, the actual payload, and space for any tag and MAC and so on. You need to do it slightly differently for decrypting versus encrypting. When you're decrypting, the first bytes of the buffer will contain the explicit IV. So you combine that with a fixed IV that you heard earlier, that you received earlier, according to the TLS spec. The final bytes in that buffer contain the tag and the MAC, or tag or the MAC, and any padding if it's applicable. So your provider needs to you need to look at the IV, you need to remove any padding and the tag and the MAC, and you need to do it in constant time. So this is here be dragons. This is quite difficult to do correctly. When encrypting, the first bytes of the buffer will be empty, and that's where you have to insert the explicit IV. Your provider is responsible for inserting the IV there, if applicable. And if it's an AEAD cipher, you need to put the tag on the end as well. There's documentation on the various parameters I've talked about on that page. So that was quite complicated for TLS 1.2. For TLS 1.3, it's much, much easier. There's nothing particularly special that needs to be done. You just need to implement the underlying cipher. So, for example, AES128 GCM, you just implement it as if you weren't specifically supporting TLS. All the symmetric ciphers are AEAD ciphers. In-place encryption and decryption will be used. So the input buffer and the output buffer are going to be the same. And you just need to support the standard AEAD parameters. So EVP, so the set tag and the get tag parameters, as you would if you weren't being used in TLS. So it's much, much easier. Okay, and that's it for Cipher Suites. I think I've just got one slide on Quick. So if you're not familiar with Quick, you haven't heard of Quick, it's a new UDP-based protocol, and it's the basis for HTTP 3. If you're using OpenSSL 3.2, there is already support for client-side Quick in there, and we're planning to implement server-side support in 3.3, which is coming out in April. The Quick protocol reuses the TLS handshake internally. So all of that provider integration that I talked about around TLS groups and signature algorithms, that all applies to Quick as well. So if it works for TLS, it will work for Quick as well. Quick does its own encryption and decryption, which is separate to the way TLS does it. It will just use the loaded providers and property query and so on to use the appropriate crypto implementations. No special Quick support needs to be included in those algorithms. So they're just standard ciphers. If Quick is going to use it, it will just use that provider supplied cipher implementation. And that's it.